today let me start this speak. This was the outline of my lecture. So far, I talked about until chapter 4, but I didn't finish chapter 4 today. And I will first continue this chapter 4 to show how the parity doublet structure. The parity doublet structure is described in a holographic QCD model. And then I will introduce some recent works on the pion condensation at the finite isotopic condensation. And then if I have a time, I will also introduce our work on the holographic nuclear upward. Let me first flash the main point of the section 4.2 from this slide. That the parity doublet structure of the nucleon is proposed by these people, which implies that the mass of the nucleon includes chiral invariant mass and the mass from the spontaneous breaking, because this is schematic, not a direct sum. But this implies that a part of nuclear mass is a chiral invariant mass, and another part of the nuclear mass is from the chiral symmetry breaking. Then yesterday I showed this parity doublet structure using a four-dimensional effective model based on the linear Sema model. But today I will show the parity doublet structure value in a holographic QCD model. Okay, then let me show how the parity doublet structure value is described in the holographic QCD model. For this purpose, I pick up the model proposed by these people. Then I put HIY, I pick up the, then I call this model HY model. And this is the Lagrangian model. And this is a five-dimensional theory. Where that the baryon here, N1 and N2 are included into so-called EKSS model. The Hardware type model, which I explained yesterday, before yesterday. Then here, this N1 and N2 field correspond to the baryon. N1 and N2 correspond to the baryon. And X corresponds to the scalar field, and okay, that the FL and FR are the field strengths of the gauge model. Okay, if this scalar field X has the vacuum expectation value, which breaks the chiral symmetry spontaneously. Okay. Then another point of importance is that the existence of two baryon fields. In the 5 dimension, fermion must have 4 components, right? And at least, it's different from the 4 dimension. In 4 dimension, that okay, in the massless fermion, you have only 2 components, right? In the 4 dimension, but in the 5 dimension, the fermion, the smallest representation of fermion has, the 4 components. Then, actually, that you don't have a notion of the chirality, right? Because the gamma 5 is a part of this gamma m. Then it means that this in one, okay, the one field transforms under the right chiral symmetry, while you need another field which transforms under this left symmetry. Okay, then as a result, this model includes, then you have 2 types of baryon field. Then actually, this will give positive parity baryon and negative parity baryon. Okay, let me perform the model expansion of these baryon fields. Okay, as I said that this N1 and N2 field, you can decompose N1 into N1L and then 1R, and N2 into N2L and then N2R by using gamma 5. Okay, this is just a convention. It's convenient to relate this 5-dimensional fermion into the 4-dimensional fermion. And then, but in the model expansion, as I will show later, that these 2 modes, 2 N1 and N2 field, will mix with each other because when the chiral symmetry is broken, this can be this N1L is mixed with can be mixed with M2L. Then mode expansion is done by using the same value. But of course, this is mode, then it's some n implies, some n corresponds to the positive value, and another set of n corresponds to the negative value. Okay, then using this mode expansion, we can obtain the equation of motion for this mode function f. And then these are the coupled equations of motion for this mode function. If we have that P0 plus implies that eigenvalue. And these coupled equations are solved by regarding this as eigenvalue. Okay, to solve this equation, it is important to fix the boundary condition. And these are the boundary conditions which we adopted. Okay, these are the boundary conditions which we adopted. At the UV, if we don't have any source term, then this wave function must vanish. Or this also that we should say that this is normalizable mode, then the UV boundary wave function must vanish. And then in terms of the IR boundary, this is some subtlety appears. One of the two modes must be non-zero at IR boundary. If both of these two states become zero at IR boundary, that means that this is only non-trivial solution, only trivial solution exists. And one of them must be non-zero. Then this is homogeneous equation. You can be that non-zero value can be anything. Then we just use one as this boundary, as an IR boundary. Okay? This does not lose any generality. Then another function, another value of the IR boundary can be anything at this moment. Then, but in the original paper by HIY, this boundary condition is taken to be zero. But they don't change the IR value. And our main point is that this ambiguity of this value of the IR boundary exists. Okay, then as I will show later, from now, this parameter plays very important role. Okay. Then, to show the importance of the parameter C1, let me show some details of the way of solving the equation of motion. Okay. Note that this M5, okay, is determined as 5/2 from the gravity sector. Okay. Of course, this conformal mass can be different, but depending on the some detailed discussion. But anyway, the simplest case that this conformal mass is taken to be 5/2, and the value of this sigma is determined from the meson sector. Okay, this is because this is EKSS model. This is based on the Hard-Wall type model, and this sigma is determined from the, for example, pion decay constant. Then P0 will be determined as a mass eigenvalue by solving this coupled equation of motion. And only the coupling G is not determined at this moment in this eigenvalue equation. Then we determine the value of G by requiring that the smallest eigenvalue P0 becomes the nuclear mass for each value of given C bar. And then G is determined by requiring P0 becomes nuclear mass for each value of C bar. Then, okay, then we regard the obtained mass eigenvalue as a chiral. Then after determining the value of G, we put this sigma equal 0, and again solved the equation of motion. I get this eigenvalue equation. Then obtained eigenvalue is regarded as the chiral invariant mass, because when the sigma becomes 0, the chiral symmetry that is not broken. In such a way, we distinguish the chiral invariant mass from this ordinary nucleon for given C1. Okay, then this is a plot of percentage of this the mass coming from chiral symmetry breaking versus the value of C1. Where this horizontal axis shows the value of C1. And the vertical axis shows the percentage of the nuclear mass coming from the chiral symmetry breaking. Then if you take C1 equals 0, which is taken by original paper, all the nuclear mass comes from the chiral symmetry breaking. On the other, if you increase the value of C1, the percentage of the chiral broken mass decreases. In other words, that if you increase the C1, the percentage of chiral invariant mass increases. Then actually for when the C1 is larger than 0.25, more than half, about more than half of the nuclear mass is a chiral invariant mass. Okay, then this is our result. But how then, whether we can determine this value of C1 or not from by fitting to the experimental data. And to do so, that we calculated, well, we obtained the mass of excited nucleons by solving the eigenvalue equation. Then this is the mass spectrum for the excited state. The blue curve shows the mass of the excited, positive parity barriers, and red curve shows the mass of the parity odd barrier. And this horizontal axis shows the value of C1, and the vertical axis shows the mass. Of course, at the ground state, we take ground state as input, then this is always 0.94. And then the interesting thing is that this structure, when the value of C1 is smaller than about, actually this is 0.12, then the first excited state is positive parity value, positive parity. While if the C1 is larger than 0.12, the first excited state is negative parity. Then this, comparing with, let me compare this with the experimental data. Okay, in the experiment, of course this is a nucleon, that the first excited state is positive parity value, but the mass is about 1.44 GeV. Then our mass is about 2 GeV. Then our model, or our approach, does not reproduce the experimental data, but okay, this seems to indicate. This means that the parity seems to indicate that some constraint appears for the value of C1. Because if we say that the first excited state must have a positive parity. But of course, this is just a model analysis, and this model is not complete because that the first excited state mass is about 2 GeV, which is too big. Okay, so this is the end of this section, chapter 4 for the parity doublet structure. If you have some question, please ask me. Yes.
So then you can conclude the percentage of the current mass contribution. Can you conclude?
Yeah, that's very difficult because if this becomes 1.5, okay, I can say something. But if this is 2 GeV, then probably it's too much to say. But yeah, I mean, it seems to indicate that most of the nuclear mass is from chiral symmetry breaking, because it's around here is very good.
Okay, in the top left figure, what happens if C1 is negative?
Oh yeah, I'm sorry that I didn't show, but this is opposite. Just this way. It is reflected. And this is actually value of the absolute value of the sigma.
I have a question. This is a Harlow model, right?
Yes.
And is there any proceeding so-called version?
I don't know exactly. Maybe, yeah, I should have checked, but I don't know.
But basically, Harlow model cannot reproduce the gradual behavior.
Yeah.
So
Maybe I should use that as a different model because, yeah. Probably, yeah, that's good. Maybe using softball model. Yeah.
I think to discuss the mass spectral correctly, so we should try so-called model first.
Yes. Yeah, that's a good point. Maybe I should ask my student to do. Okay, let me move to the next chapter, where I studied pi condensation and finite ice-beam computation. Because this is complete, this topic is as different from the topics which I talked so far. Then let me start from again at the introduction by showing this. Okay. Here the horizontal axis is the biochemical potential, and this axis is temperature. Okay, usually in this area that people usually use this phase. But here I'd like to add another chemical potential, which is called ice-beam chemical potential. Ice-beam chemical potential, you can easily imagine that because proton and neutron carries ice beam. Then this baryon chemical potential, the baryon number charge is same for proton and neutron, but the ice beam number is different for proton and neutron. Then if you have, for example, neutron-rich matter, that matter has ice beam chemical potential. Then actually studying this direction is very important for studying the asymmetric nuclear matter. So then the experiment is run in Japan and Korea. And also that also it's very interesting to study this direction to know to get the information for neutron star. As you may know that in the recent years that neutron star with mass of twice of solar mass was found, and most of nuclear model cannot explain this high mass. And it may be interesting to study this direction. Also, this to explain the neutron star with heavy mass. Okay, but here I'd like to concentrate on this biocondensation phase, where that ice-beam chemical potential is large. Okay. Then, as you can imagine, ion is the lightest particle with non-zero ice beam. Then, if you increase the ice beam chemical potential, then ion condensation occurs because this is just a simple Bose-Einstein condensation. Then, if you increase the chemical potential, that lightest particle having charge with lightest meson or lightest boson having non-zero ice beam condense. This is simple idea. But the point is whether that is a first order or second order phase transition, or what is a critical exponent, what is and so on and so forth. There are several questions. Actually, pioneering work is done by using this chiral Laplacian at order p square, means the leading order, by these people. They show that the phase transition from normal phase to the pion condensation phase is second order. Namely, that here that the horizontal axis shows the ice beam chemical potential, and this vertical axis shows the ice beam number density. Then this shows that when the ice beam chemical potential, okay, when the ISP chemical potential is below the pyromass, then the number density is 0. Then when the ISP chemical potential is larger than the mass of pyro, the number density starts to grow. And this is actually the chemical potential dependence of the number density. And they show that this is actually the second order phase transition. And in this talk, I will introduce our recent work where we studied the pyro condensation, this structure, using the hard-wall QCD model. Okay, how this looks like in the hard-wall model? That is a question. Okay, then this is the model which we used in our analysis. Of course, this is ordinary hard-wall model, which I explained in the first day. And then to study the pyro condensation phase at the highlighted ISP chemical potential, we introduced the beam field, which are uniform in 4D measure. Then ISP chemical potential is introduced as a UV boundary value of the gauge field. And this preview, for the finiteness of the discussion, I will restrict myself to the two flavors. This gauge field review is given by 2x2 matrix, corresponding to the two flavors. The review is given by the sum of 4 components. Okay, this is corresponds to the omega meson. These 3 correspond to the rho meson. Okay, the ISP chemical potential is introduced as a kind of boundary value of the rho meson, neutral component of rho meson. Then the beam field are determined by solving the equation of motion in the 5 dimension. This is Lagrange, then you can get the equation of motion, and you can solve it. Then you can study what's going on. However, that if you use all the beam field, it is a bit too much complicated. Then we adopted several answers. And these are the answers which we adopted. Something wrong. Okay, maybe something wrong. Okay. We assume that all 3 special rotation symmetry is not broken. Because that's a pyro is a pseudoscalar boson, then carrying speed 0, then even if the pyro condenses, then the rotational symmetry is not broken. Then we assume then, of course, if you increase ISP chemical potential, for example, about get to the 1 GeV or something, then rho meson should condense. Then we can study only the when the ISP chemical potential is small. But in that case, we can even assume that rotational symmetry is not broken. Then we say that the B field for this vector and action vector component is 0. Also that we assume that the eta meson doesn't condense, and also A0 meson doesn't condense. Okay, because this is as follows. Okay, eta meson doesn't carry the ISP, because eta is the ISP signal. Then probably will not condense, then we assume that eta meson doesn't condense. And also A0 meson mass is at least 980. Okay? This is a lightest A0 meson, lightest isotriplet meson. Then when the ISP chemical potential is smaller than this, we can even assume that this meson doesn't condense. Then we take this and this to be 0. Okay? This is our assumption. These are reasonable assumptions, and in addition to this, we adopt these others also. And a part of equation, this is a part of the equation of motion for neutral pyro and neutral action vector meson and charged rho meson. Okay, this is hard to see, but anyway, we can show that actually vanishing four components give a set of solutions. Then we assume that all of these vanish. Okay, please note that strictly speaking, we have to check whether this gives actually minimum of the potential or not. But we don't, because the vacation motion, a couple of vacation motion are too much complicated, and we assume that this is zero. This is in some sense, I think that this is also a natural assumption. Anyway, if this is true, that the neutral pion doesn't condense, even for the mechanical potential is larger than pi. Okay, only charged pion condense. If these others are included, the Lagrangian for the relevant mean fields is reduced to this one. Okay? There are only 5 mean fields. Okay? One corresponds to the isosecret scalar. Okay? This condensation exists even at vacuum because this is this wave of this isosecret scalar corresponds to the Q by Q condensate. And this B corresponds to the pion condensation. And the theta and theta correspond to the time component of action vector method, and the phi corresponds to the neutral row method. Anyway, these 5 mean fields are introduced, and solve the complication motion for this. We solve the complications motion for these 5 components. This table shows the boundary condition. Anyway, as in the case of vacuum analysis, I said the UV, this component takes this value. Okay, this theta equal to I12 is just for convenience. This theta equals 0 at the UV, then this is 0 is 0 at UV. And this is the standard, these are the standard higher boundary condition. Okay, this higher boundary condition which I showed before. And this is the equation, these are the coupled equations motion for these 5 components. And using this 5 components, we can calculate ISP number density in this way. In our work, we solved the complication motion to calculate the ISP number density using this formula. Okay, then this is our result for the relation between the ISP chemical potential in the horizontal axis and the ISP number density vertical axis. Here the green, red, and blue curve shows the result for different values of lambda. Lambda is a parameter to describe boundary potential. But this is directly connected to the isotriplet meson mass. Okay. When you use this isotriplet meson mass as input, lambda is determined to 4.4. However, in this model, only the Q-type scalar meson is included. And some people argue that this meson is not Q by Q. This is made from Foucault. In that case, we cannot use this as input. Then we also change the value of this lambda from 1 to 100. But these are the corresponding isotriplet scalar meson bars. Anyway, for any choice of parameters that these parts are same, there is small deviation in this part. But anyway, one point is that you can see that all of these results show that second order phase transition here. Okay? And also that critical ISP chemical potential is same as a pion. This result is consistent with the result obtained by the Carrel Lagrangian